Be moderating this session. First up, we have Brian Rohrback. He is the president of Infometrics. His education, he says he's still working on it, but he has a PhD in oil chemistry along with an MBA. He worked for Citgo running an exploration and production lab. He was reassigned as an exploration geologist, geochemist for Europe, Africa, and the Middle East, and ended up the manager of planning and budget for the same division. He assumed presidency of Infometrics and for decades have helped guide the product and service development primarily for downstream, both in process and in the lab. Also, key is integrating chemometrics machine learning for the process and laboratory instruments manufacturers. His hobbies include giving presentations like this and classic British sports cars. Everyone, Brian Rohrback.
Thank you. Okay. So, I've traveled around a lot. I've gone to a lot of refineries, I've gone to a lot of chemical plants, I've seen a lot of implementations. And because my company deals in optical spectroscopy calibrations, I thought, I see some of the same mistakes over and over again. And so what I thought I'd bring to you is a little bit of an education purpose. I'd like to talk about error and the errors that are associated with the optical spectroscopy process and how they can be controlled. So this will work pretty much for anything. So the first thing I want to do is just point out that we have two parameters that we're looking at whenever we're dealing with any kind of analysis. And one of them is the precision of the analysis. The other one is the accuracy. And sometimes these get confused. So I'm going to eliminate all the confusion. And there are ways of figuring out what the precision is. I mean, you basically repeated a measurement a number of times. You've got a pretty good idea what's going on. So if we were going to do an analysis and we were able to get the same answer over and over again as is shown here, we have something that is both precise because we see the same result each time, and it's accurate. It matches whatever reference value that we're dealing with. So this is what precise and accurate looks like. But sometimes, in fact, most of the time, the way you start out, you've got something in optical spectroscopy that's very precise. But it doesn't necessarily give you the right answer right away. It has to be calibrated. So here we have precision but no accuracy. The other thing that can happen is that you've got, say, we'll take oil company refinery example. You've got an octane engine. The octane engine is an example of something that is not precise. You're going to see variability in that number from run to run, even of the same sample. In a situation like this, you know it's not precise. You don't know whether it's accurate or not. This is going to be important in a second. Seconds up. This is an octane engine. So what we're going to look at is we're going to see a series of values that are going to be measured, and we're going to get basically a Gaussian distribution that's there. We can talk about standard deviations for that, and roughly you're looking at a 2 sigma or 95% confidence interval that spans about an octane value. So that's the engine we're dealing with. Some labs are better than others. Some systems are better than others. So let's think about how we're going to take an optical spectrometer and match it to an octane engine. So if this is what the octane engine represents, and consider we're using it to define octane. So, hey, this is the number we got out of the octane engine, that must be true. But the point of calibration is we're going to take that set of spectra that are off on the side, and we want to simply move them to the center of that distribution. That's the idea behind calibration. But in practice, what we have is we have that spectrometer sitting there, and we're trying to match it up to that octane engine. So really what we have is we have a whole bunch of spectral data that are very precise that are going to be mapped to values that are not as precise. That's what we're doing in the process. Well, we can still do something about making these measurements more accurate. So if we have a calibration system that I've shown before, that's the mapping we're doing. The alternate that we have is we could take the spectra of a single sample, and instead of using it, we run that octane engine, in this case 4 times, we can take the average of that, and that actually improves the precision of our measurement by a factor of 2, so it's the square root of 4. So that is one thing you can do, and that's something that nobody does, because no one wants to take the same samples and run them over and over again. But there are other things that we can take advantage of, and I'm going to take an example that was actually presented at the ISA-AD, so that was the earlier name for ATC, and just give you an example of what would happen if we had a reference value error, but a spectrometer error that was significantly higher. So in this case, we're 3 times higher. And what you see is the standard error prediction, which is the gray line down at the bottom, is representative of that combination of errors. And you can see it's actually very close to what the spectrometer error is in this case. So look at that plot, and as we reduce the spectrometer error, you can see that everything kind of coalesces into the middle. So now we've got something that's a very small spectrometer error, and you can see that the standard error now looks a lot like what the reference value error is. If the spectrometer error goes away completely, then the standard error prediction is identical to the reference method error. So that's what you have. What I then hear in the industry is the model can't be better than the reference value. But that's not true. What it means is we can't target a number that is smaller than the reference error, but the true reference error or the true spectrometer error is significantly smaller. So let me show you how that works. We're going to take this plot of data, and just for fun, I'm going to rotate it around. So as we rotate this, and I'll move it off to the side because I have something else to say. That looks a lot like a Gaussian distribution. If you take all those points and drop them down to the baseline, you're going to get a Gaussian distribution of points. Whenever you look at a Gaussian distribution, what do you say? Best value is that apex. That's represented by the line, the regression line that we have for doing, in this case, octane. So what we have is a way of squeezing down the error, knowing that we have a more precise measurement in the mix. Now, whenever you're dealing with the issues of accuracy, precision, or error in general, there are actually 4 places where this comes into play. And if you were old enough, I would say something about Monty Python, because I can always think of a 5th reason too. But you have a choice of spectrometer. Perhaps a Raman spectrometer, perhaps a near-infrared spectrometer is going to be best for a particular situation, particular parameters that you're doing. They all have limitations, so you have to understand that, but that's one of the sources of error that's going to be in place. One is in the method development, so actually choosing the preprocessing that is going to be necessary, choosing a wavelength range that will be necessary, choosing even the algorithm. And I'll show an example for an algorithm choice in this. Then we have this topic of model maintenance, because that's the place where actually you have the most control over it. And there, the issue is human error in building a calibration model. And then finally, an error understanding. So how do we compensate for the problems in the reference method? Because those can be compensated for in real time. So in method development, here's an example of 700 experiments that were run to find the optimal processing for asphalt in this particular case. And this one actually, things break out pretty easily. So what you're seeing is a series of experiments, and each of those lines represents one kind of pre-processing. And then the dots represent different numbers of factors to figure out what's going on. So basically what you want to do is look for the lowest point. This case, there's one pre-processing that seems to outperform everything else. The lowest error is marked by the triangle in green, but all the points that are in blue are statistically insignificantly different. And oftentimes what you would do in a situation like this is you would go to a more parsimonious model, something with the fewer factors, so it's less complex. As it turns out, if you go through then later, as we tend to do in our model management, routine model management, you find that the optimum is actually where the star is. So that's looking at the optimizing the actual samples that were used for a model. And that's actually an easy case. The harder case is one like this one, which is an octane case, where you see these things are all mung together. So taking that, blowing up a certain section of it so that you can see more about what's going on, you can choose a pre-processing technique that gives you a best answer. And in fact, the answer that would be chosen in a situation like this is the more parsimonious method. The other thing that you can do is you can look at the algorithm that's associated with it. And one thing that you will see, and I'll tell you, PLS is kind of the workhorse. You can always rely on PLS. PLS has the advantage that it actually assumes that there's error both in the reference method and in the spectra. If you were to take locally weighted regression or PCR as a mechanism, it makes the assumption that all the errors in the spectrum, none of the errors in the reference value from the lab. That makes the lab people happy, but no one else. So we know that PLS is a workhorse, but sometimes you find that there's a little smile in your data, there's a curvature, and you can do things like take a series of models that would be moving through. So this is what is called locally weighted regression. It's a way of quickly merging models. And so by doing that, when you have a new sample that goes in, you just poll the nearest neighbors, and then you use that model. So the optimization in this particular case is you choose the number of nearest neighbors that you're going to use for the model, and then again, like you do in other cases, you choose the number of factors. What you get as a result is you get more of a map. So now we have a whole bunch we have a minimum, which is there now in red, and a series of points that are in blue that are not statistically significantly different from that. And from a logic standpoint, then the choice should be either take the minimum, number one, take the number of neighbors from the minimum, and then find the lowest number of factors that you would use, which is number two. Or actually my favorite is find the contiguous, look at the contiguous values, and then I pick number three as the best possible model. It is the one that has the lowest rank and the highest number of neighbors at the lowest rank. What then you get is that original data that you see up here on the left. If you're using a locally weighted version of PLS, then that straightens it out. And you can see that it reduces the error fairly substantially. And if we were to take that calibration and apply it to a prediction set, you can see that the numbers continue that way, so they get better. So we know that we can choose optimal preprocessing. That's going to reduce the error at times. If you've got curvature in the data, that using a locally weighted model is useful. And remember, this is something you do precisely once. You will never do this again in the life of the spectrometer, and it probably will take you about 2 days to do. So we've shrunk the error that's associated with it. So now we move into the kind of routine maintenance world. In the maintenance world, the whole thing is all about how do you handle a bunch of data. I've got thousands of spectra now that are coming through. I've got maybe tens or hundreds of runs in a laboratory. I need to be able to process that. And there are standard procedures. There's a standard way of doing it. There are best practices for doing it, and those are well defined. But you should always build a validation set so that you can make sure whatever you're doing is correct. So we have set standards for best practices, and those can be completely automated. So this is where chemometrics kind of blends into machine learning. So I mentioned before that one of the issues is really human error. Because what happens now in processes, when I started teaching the chemometrics process to people, we've taught thousands of people. There were very few spectrometers out there, and usually people were very involved and would take classes. Now it seems like a lot of companies don't have any time for taking classes, and people that are coming in don't have expertise in multivariate statistical analysis. So it kind of becomes a point of inconsistency. But I thought what I'd do is I'd just show you in a blast, going through and taking a Ron model and just optimizing it. Here are all the steps that are done in an automated system. So you're doing some evaluation in this, and it does those evaluations in order to come up with an answer. And what we found is this approach actually beats humans every time. There's a test that was done where we had a set of 6 different models to be generated. They were a combination of near-infrared and Raman data. And they were sent to experts in the field. And we asked them to do an optimized model and then compared the results. And what you see is, and I will say, all the experts that you see listed here have PhDs in the process, and 2 of them have written books on how to do it. So by having a consistent mechanism for doing best practices, you can outperform humans. And it's faster. So if you have, say, 700 samples in your data set, it takes a little over a minute to do the optimization. So there's almost no reason not to. So now what we see is maintaining the calibration models. That's critical to do. And what we can do is now shrink our error bars. So now we've got the best error that we can have there. But we still haven't taken into consideration what's happening in the reference values. So if you have a means of collecting data, you have to do this anyway. Run the same sample a bunch of times. How many times did you run it? What was the standard deviation of that? And if you have that information, then we have one more thing to do. Choose a probability limit to avoid overcorrection. So if we were to take a situation where we have a 5% possibility of overcorrecting, you get a distribution curve of a factor here called K that can be used to modify it. Basically, it is just the proportion of the error that you see that is going to be subtracted from the final answer. So you can see with roughly 10 samples in your replicates, about half of the error goes away. So it's represented by your reference value. And if you need the equation, actually look at the paper that's associated with it, and it gives you the equation. It's pretty simple. And here's what it means in a typical oil refinery. So we have just a series of samples that were there, what the final number of PLS factors were for this particular set, what the observed error and what the total true error were after the corrections. You can see basically 25 to 50% reduction in error. So by accounting for the error in the laboratory values, you can estimate the true error in your measurement. And you can use that to move closer to what your diagnostic is, what you're trying to do with your data. So the idea is to reduce giveaway in this. And it does provide you with the best possible assessment of the calibration quality. So we've shrunk it now further. So the end of this is, just keep in mind that the reference value has uncertainty. It is not a precise number. It is something that you can handle by running it a whole bunch of times, but no one ever does that. But we essentially have the power of multiple samples by running a bunch of different samples, even if they're getting different reference values. And using that information, you can tune in onto what the true error in your system is. So everything is tied to, pick the right instrument, pick an appropriate pre-processing method, do locally weighted regression if you've got curvature in your data, and then use a machine learning approach to avoid human error in the routine calibration issues. And then at the end, actually at the beginning too, factor in the reference uncertainty. Because if you do that, then you're actually getting a better picture of what's truly going on in your process, and I think that's the point. So with that, the only thing I'll say is if you want to discuss this with me further, I'm in booth 420. And it's not so big that you can't find anybody, even without a number. So that's what I have to say. Thank you.
Do we have any questions for Brian? So next up, we have Gregory Shahnovsky, if I'm pronouncing that right.
Almost.
President of ModCon Systems. Graduated from Azerbaijan Institute of Petrochemistry, followed by postgraduate studies specializing in automation of petrochemical processes. Later pursued advanced education at the University of Haifa, specializing in business administration for high technology enterprises. He began his career at ModCon in 1990, progressing through roles such as service engineer, applications engineer, and deputy general manager before being appointed CEO in 2015. He assumed the position of president of ModCon Group. Hobbies include yacht sailing and traveling.
Thank you so much.
Thank you.
Good afternoon, everybody. My name is Gregory Shahnovsky. I'm working for ModCon Systems. And basically, our company is dealing with process analyzers since early 70s. And during this time, we were working with companies like Combustion Engineering, Applied Automation, Beckman, Precision Scientific. I am quite sure that young people are not familiar with many of these names. But that was actually the beginning of the process analyzer technologies development. And during all this time, our main task was to get these analyzers integrated as a complete system. So what basically we were dealing with? First of all, with sample systems. It's very important to build the reliable sample system, which includes sample probes, sample lines, sampling conditioning, recovery systems. Without all these devices integrated together, your analyzer simply will not perform. And secondly, to get everything integrated inside the housing, which takes care of environment, of safety, of many other issues, which are very important parts of this project. And we can say that every analyzer's project basically includes approximately 70% costs related to the system integration, and only 30% of this investment is related to the analyzer. So it's a nice business, very profitable one, but we decided to look for alternative solutions and to try to develop technologies which will enable you to reduce the requirements for sample systems, or probably even to eliminate them, and also to reduce your requirements for the housing. and probably even to eliminate these requirements. So what actually I'm going to describe here is two solutions, okay, from many solutions developed by Modcon, which can help you to eliminate these problems and hopefully to make your process analyzers project relatively simple. The first solution will mainly describe technology which enables you to install your analyzer in the control room and then to connect it to the sample probes located directly in the process using fiber optics. This solution will not require housing, and this solution also will not require sample systems. Second solution will describe analyzer, which can be installed directly in the process without housing and without sample systems, simply because it was designed using technologies which enables us to withstand with very harsh environmental conditions and also process requirements. Before we start, it's very important for us to distinguish between two primary categories for process analyzers. The first category is actually including conventional analyzers. Okay? By conventional analyzers, we mean technologies which comes from the laboratory. So normally, these technologies are related to wet chemistry, to gas chromatography, to many other technologies which are based on the standard methods. And using these technologies, we can be absolutely sure that our results will correlate well with the laboratory results because basically we're using the same technologies. The second category of these analyzers we call correlative analyzers, which means that we're using something which doesn't have any relationship to the laboratory method, but we are trying to find a relationship between what we measure and the results which we're getting from the laboratory. The approaches which we are using here are very different, and it's important to understand these two categories of the analyzers before we describe solutions which were actually used by us in these two technologies. Optical spectroscopy during the last 40, 50 years were significantly changed. I think that the main reason for that was the computing power. We have today more computing power. We are capable today to process information in significantly more complicated way than we were able to do 40 or 50 years ago. If somebody remembers the Western research air demand analyzers, which were used for many years successfully in sulfur recovery processes. These analyzers were based on analog electronics, which took care about the data processing from the H2S and SO2 photometers. Now, the important thing to mention here is that when we measure H2S and SO2, we have to take into account the sulfur vapors. These sulfur vapors can significantly change the spectrometry of the signal we are getting, and these concentrations have to be taken into consideration. Now, because these analyzers were based on analog electronics, it certainly was not possible to build a complicated matrix or systems based on modern machine learning in order to take into account these concentrations. And the analyzers we are talking about were including the special condenser, which was used to maintain the constant temperature of the sulfur. And in fact, we were trying to establish equilibrium with the constant sulfur vapors content, which can be compensated. It's very complicated, okay, to build such a system. Such a system requires a very serious and extensive maintenance. And if you take the modern air demand analyzers, okay, manufactured by Amitec, okay, who is actually one who is owning Western research today. You can see that this analyzer doesn't include condenser, simply because we can compensate for sulfur vapors using the mathematics. So those are the changes which we see in optical spectroscopy. And saying that, I have to mention that that was the main reason why we decided to be focused on these technologies. And the first system we were dreaming about was system which is sitting in the control room, in the very safe environment, air-conditioned rooms, without any precautions related to the hazardous area. And these systems will communicate with the sample probes located somewhere in the process, such that these sample probes will not include any electricity. That was a dream. And in order to develop such a technology, it was necessary for us to carefully evaluate all the necessary methods, including the near-infrared. Okay, now let's talk a little bit about near-infrared. Near-infrared technology basically goes from 700 to 2,500 nanometer in the spectral range. And we say that this range enables us to see approximately 80 to 90% of the hydrocarbons spectrum. Now we have first overtone, second overtone, and third overtones in this spectrum. The most popular one is the second one. Second overtone already includes approximately 70 to 80% of the information about the hydrocarbons. Third overtone includes even less, between 60 to 70%. And in our opinion, this overtone, this third overtone, was somehow underestimated because it did not include the same information which we had in the second overtone. However, it appears that third overtone enables us to transfer the information, the spectral information, using the standard telecommunication fiber optics, which is not possible with the second overtone, which represents a kind of opportunity we decided to seriously consider, and finally to develop a system which will include less information than we may have in the second overtone, but will include significant improvements in the software, which will compensate for this information discount. The system we're talking about is commercially available and already used by many refineries. And basically, we're talking about the technology which enables us to install the analyzer in the control room while the sample probes are located directly in the process. The communication between this analyzer and sample probes is done using the standard telecommunication fibers, and the maximum distance between them can be up to 2 miles. That means that we can put one single analyzer in the control room and get connected to many sample probes located within the refinery. Today, we have many refineries who are already using this technology successfully, and very significant fact here is related not only to the fact that we do not have housing, we do not have sample system, we also need a very little effort for maintenance, because to maintain the models for the third overtone is much easier than to maintain them for the second overtone. So this is actually the first solution, okay, which I promised to describe, and which eliminates the need in the housing and in the sample systems, which finally means that the end user is only buying the analyzer and installation of this analyzer. And this installation doesn't require any additional equipment or any additional investments. We have another solution in our portfolio, which unfortunately still require analyzer housing, because here we're talking about the sample streams which are heavy and opaque. So until today, we were not able to use the third overtone for these very complicated samples, and therefore, here we are working in the third overtone. I can tell you that we are working hardly in order to enable also this technology to be transferred into the solution, which will not require installation in the field. As we know well, and it was very well described in the previous presentation, the using of spectroscopy technology, I would say the challenges related to the using of the spectral technology are mainly related not to the hardware, but to the software. It requires a very significant effort to build the models, and then these models have to be properly maintained. So already in early 90s, we have developed the first software, which enables to make corrections of these models automatically. During this time, it was done in a very simple way, okay, using PLS, when our system was looking into the laboratory results through the DCS and was changing the analyzer readings using the deviations, okay, which were observed. So in fact, we were talking here about the bias, which was very effective. I can tell you that many refineries are still using this technology and are not interested in any more sophisticated solution because it works. Because it works, even it's not the perfect way for how to solve the problem. Today, we have a more powerful solution, which are based on machine learning. And this powerful solution enables us to not only use the bias for the models correction, but also to rebuild these models. We can rebuild these models using one single additional sample, which was observed as one which does not have the required agreement with the analyzer results. So once we see that there is a kind of disagreement between us and the laboratory, this software enables us to take this sample, this specific sample, from the laboratory results and to rebuild the model so that the model will become significantly more accurate. And this technology certainly gives us an additional degree of freedom when we're talking about the model's correction. Automatic model updates today is possible. We already have quite a few examples of very successful implementation for these technologies. Saying that, I have to mention that once you can update your models automatically, you can also build them automatically. And this is a very significant step forward, especially for refineries who are still using their own resources for model building. And these resources are very expensive and sometimes priceless. Today, you can find, let's say, less software people who are working for refineries, and you can find today more and more software people who are working for Microsoft or Google. And this is also something which we have to take into account when we're talking about the model updates by the very experienced staff within the refinery. The second solution I promised you to describe is absolutely different from the solution we have discussed right now. And this solution is not already designed for petroleum industry, not for liquid, but for gas. Okay, so the necessity, okay, to develop this technology came from one of the hydrogen electrolyzer producers who explained to us the very fundamental problem they have with the oxygen measurement. All the available technologies, okay, for oxygen measurement requires sample extraction, pressure reducing, kind of conditioning, measurement, and then venting. Okay, so for hydrogen production, venting is a big problem. And therefore, they asked us to find solution which will enable them to measure oxygen at a higher pressure directly in the pipeline. The research, okay, which was done by our scientists, have defined the technology which can be considered here, and that was fluorescence. So using this technology, we have developed an analyzer which can be installed directly in the process with stands with the higher pressure up to 200 bar gauge. Certainly completes with all the requirements as related to the hazardous area, ATC, ATC, and so on. And what is very important, this analyzer is also SIL 2 approved. Why? Because by the way, to get SIL 2 approval today is not a big problem. Okay, you can do it, but the main problem will be with this analyzer installation, because once we have sample system which delivers sample to this analyzer, the SIL 2 approval is automatically canceled. Okay, so here we were thinking about solution which will not require sampling and also will not require housing. Okay, so basically this is how this analyzer works. You can see that this analyzer installed directly in the process. By the way, you can see this analyzer here. Okay, if somebody will be interested later on, you can come over and see it with Greg. And basically, this technology today enables us to solve problems which wasn't possible to solve before. Does not require sampling, doesn't require housing, and the total investment certainly is significantly lower, okay, than one which cannot be installed in situ. Response time, very critical issue. Okay, so having your analyzer installed in situ and without dependence on the sample lines, filters, and other sample system accessories, you certainly can reach significantly faster response. And this is very, very important. Just as a conclusion, we described two solutions from many solutions which were developed using the photonics and software, okay, which actually used in these applications. And these solutions already show us that there are always additional opportunities for development. We did not see, let's say, very significant changes in the analytical technology during the last years, maybe because we did not consider already existing technologies which can be used in different ways. And that's actually what we're trying to do today, okay? We are not developing new methods, okay? It's quite challenging, to find something different from all the existing methods, but we are trying to use the existing methods and with the software, okay, which today is significantly more powerful than it was yesterday, to build solutions which finally enables us to solve problems which we believe are important to be solved these days. This is my presentation. Thank you very much. If you have any questions.
Any questions for Gregory? Thanks, Gregory. Last but not least, we have two presenters today for this paper. We have Mr. Rod Merz. He's with Amatec Process Instruments. He's the RSM, Regional Sales Manager for Canada. Education includes chemical technologist and North Alberta Institute of Technology. Rod has spent close to 35 years in the analyzer world, in both the lab and process analyzer worlds. Rod has worked with Dow Chemical, Varian, Vanco Analytics, and for the past 11 years, Amatec Process Instruments as a regional sales manager for Canada. Rod also sits on the board of directors as vice president for the Alberta Sulfur Research Limited, a globally recognized nonprofit research facility affiliated with the University of Calgary that provides both core and contract research for many of the corporations today. His hobbies include golf, playing guitar, photography, and growing orchids. And also we have Mike Smeltink. He's with Worley Caprimo. He's the Director of Business Development. He has a Master of Science in Chemical Engineering from Delphi University of Technology. Mike is the Director of Business Development with Ben Worley Caprimo, with a solid engineering background in the field of gas treating and sulfur recovery technology. He is responsible for business development of sulfur recovery units, tail gas treating units, gas treating units, and related process in the geographical areas of North and South America, and has been in the industry for nearly 20 years. His hobbies include hiking in the Rocky Mountains. Thank you.
Thanks, Bobby. So we're going to talk about, as the title says, second generation SRU feed forward control analyzer air control technology. It's quite the mouthful. We've broken it up into two parts. I'm going to cover basically the sulfur portion, the SRU portion, and the analytical aspects of it. And then Mike's going to take over and talk about how we merge all those into improving your sulfur recovery system. My portion's essentially an overview of the measurements for air demand. So basically everything we're going to talk about, or I'm going to talk about, all revolves around the role of air, or in other words, oxygen, in the sulfur recovery unit. I apologize, I do have some cheat sheets just to keep me on track, otherwise I tend to wander. And basically the comparison between traditional feedback control that's traditionally been in use for many, many years, and a more modern approach, which is feed-forward control. And then the next step in that is automated feed-forward control, which Mike is going to delve into in much more detail. So, sulfur. A much needed element that we use for many different things, usually in the form of sulfuric acid. It's used in mining, metals, battery production, all sorts of chemical and petrochemical applications. And up until probably about 70 or 80 years ago, the only real source of sulfur was through mining. And with the invention, I will call it, by Carl Friedrich Claus back in 1884, we had the Claus reaction, which is essentially the combustion of H2S with oxygen to produce sulfur as a byproduct and SO2. Unfortunately, batch process doesn't work really well for continuous modern chemistry. So in the 1930s, I.G. Farben, as part of the German war effort, came up with the modified Claus process, where we break it down into two different reactions. Essentially, we combust a third of the H2S with oxygen, and then react that SO2 product and the H2S to produce sulfur and water as a reactant. A couple things that are important about this. The reaction is somewhat bidirectional, so unless you remove the reactant products, it only achieves about a 60% completion rate. So it's important that we continuously remove the sulfur to keep moving the reaction forward to increase efficiency. So basically, the first stage of the modified Klaus process is a thermal stage. So you can think of it as a combustion. We used to technically call it a reaction furnace, but now we call it a thermal reactor. But essentially what we do is we bring in the H2S and air and combust, for all intents and purposes, a third of the H2S and create our ratio of 1 part SO2, 2 parts H2S. That is highly exothermic, so as you can see from my upper reaction there, you get about 520 kilojoules out of that thermal stage. And then the second part of the reaction is actually catalytic. So again, it's also thermal, but not nearly as high temperature. And we do that in what's called a sulfur recovery unit. And unfortunately, this pointer doesn't show up on the screen. But unfortunately it doesn't. You can see that at the front end of the sulfur recovery unit, we have a thermal reactor, and that's where the thermal stage occurs, where we combust a third of the H2S. And then the catalytic converters are where the second reaction occurs over a catalyst bed, typically of alumina. It's important, again, like I said, that we remove the sulfur product so we can continue moving the reaction forward. And those are basically the condensers that sit underneath. Actually, I wonder if my cursor works here. No, it doesn't. The condensers remove the sulfur and allow the next catalytic converter to continue on pushing the reaction forward. It's really important that that ratio of 1 part SO2, 2 parts H2S is maintained. If you go off that ratio, you start to slide quite a steep slope in terms of your recovery efficiency. And as a result, back in the late 60s, early 70s, we saw the development of the tail gas analyzer. My company, Amatec, who bought Western Research, was part of that as the Western Research and DuPont groups. So the tail gas analyzer was essentially a feedback control mechanism. Essentially what would happen is you would look at the end reactants at the end of the process and adjust the air coming into the reaction furnace accordingly. The issues with that is that there's a significant lag. You've got about a 20 to 40 second lag from the front end of the reaction furnace all the way to the tail gas analyzer or air demand analyzer. So it's a rather slow way to adjust. Plus, the amount of control that you have is typically regulated to about 10% of the air going into the sulfur recovery unit. So it's slow, it doesn't have a lot of adjustment capabilities, but typically in a refinery, you don't have a lot of variability in your H2S stream coming in. So for a refinery application, it's pretty suitable. In the natural gas world, typically you can see dramatic variations in the amount of H2S coming in as you bring in new fields or shut in fields. That essentially means that you could have variations, significant variations in your H2S content coming into the plant. So it was, I guess, a matter of practice that you would put an H2S analyzer in front of the sulfur recovery unit to just kind of keep an eye on what the changes in H2S going into the sulfur recovery unit were. So all well and good. The downside to all of this is that there are potentially other reactants that can come into play. If you have any hydrocarbons whatsoever coming into the plant, they will preferentially react with the air coming in. And as a result, you're going to go off ratio. So you can kind of think of it in a way as long as you're maintaining that optimal ratio, you're going to maximize your recovery efficiency. As soon as you move off that ratio, things like your emissions are going to go up. If you have a tail gas treater unit on the back end of your plant, you can do damage to the amine, or if it's a superclaus plant, you can have thermal excursions. All sorts of bad things can occur by having a dramatic swing-off ratio. And as I said before, the important part of this is that the tail gas analyzer actually has a fairly limited range of motion that it can control within that reaction set. Hence the development of feed-forward control. So feed-forward control is basically looking at all the constituents going into your sulfur recovery before the thermal reactor, and being able to adjust the main air rather than the trim air, so that 90% of the air coming in that the air demand analyzer doesn't control. The big reason for doing this is that small amounts of hydrocarbon have a big impact. So as you can see on this slide, the number of moles of oxygen per mole of hydrocarbon goes up pretty dramatically as the molecule gets larger. And you can see the ratio of oxygen required per mole of hydrocarbon versus a mole of H2S is even larger. So the impact of a slug of hydrocarbons coming over from, let's say, over-circulating your amine or having some sort of upset going into your sour water stripper can have a very dramatic effect on how much air is required to maintain that 2-to-1 ratio for H2S and SO2. So as a result, part of the feed-forward analysis control basically means that we want to look at all the reactants coming in and account for how much additional air we would need in the case of a potential hydrocarbon slug or variations in H2S coming into the plant. Now, in terms of technologies to measure hydrocarbons, there's lots and lots. Unfortunately, a lot of them are slow or extremely expensive or not necessarily suited to the environment that we see in the feed into a sulfur recovery unit. Basically, I think pretty much everyone is settled on the approach that UV-Vis spectroscopy or UV-IR spectroscopy is the fastest way to do an analysis. Chromatography is too slow, mass spec a little too messy to maintain for these types of applications, et cetera, et cetera. So what we look at is in the UV, we can look at the H2S, we can look at ammonia if there's any coming in. In the IR, we can look at CO2. If we need to do mass balance, we can look at water. But more importantly, we can also look at the total hydrocarbon content. By looking at the range from about 3,100 nanometers to 3,500 nanometers, we're looking at the carbon-hydrogen bond that's typical in all smaller hydrocarbons. And from that, we can infer roughly a total hydrocarbon output as either methane, ethane, propane, whatever is appropriate for the specific plant that we're dealing with. This is important in that we can then adjust the main air coming into the plant and control the reaction so that we still stay on ratio with our air demand in relationship to the H2S, so we can still maintain that 1/3, 2/3 ratio. The other thing that I'll point out is that I mentioned we can output it as methane equivalent, ethane equivalent, that sort of thing. It's important to know what's more appropriate to your plant. So in a refinery situation, we could have typically heavier hydrocarbons coming through, so we might want to do something as a methane or even propane equivalent, whereas in a natural gas plant where some of the slip might be methane, we would want to do a methane equivalent. And you can see here, this particular graph was calibrated with an ethane calibration for a hydrocarbon response at 3.3 microns. And you can see the ideal versus the actual measured using ethane as the cal gas. So we output, for example, in the black, the bottom little stars are what methane equivalent output would be if we measured total hydrocarbon as methane, but actually got an ethane slug in. You can see that the ethane in red is right on course. And then it works out better for the larger hydrocarbons just because at 3.3 we get more of a response from the larger hydrocarbons. But needless to say, the goal is to make sure that we match to your specific process, that we output the appropriate hydrocarbon output so that we control the air properly. One last word. None of this is really applicable if we're too slow or if it can't be done safely or if it's not reliable. So we firmly believe that the sample conditioning should be done at the sample tap point. We've developed a specific probe for that application. We keep it heated so that it's above any ammonia salt formation, in the case of sour water stripper gas feeds. And it has a built-in membrane filter to shed any liquids, and essentially, as I said, we keep it hot to ensure there's no condensation issues. It also feeds back into the process from that location so that it's a continuous sample loop. It's got a built-in aspirator. So essentially, with double block and all those features, it's fairly easy to maintain and safe and reliable. So at this point, I'm going to hand it over to Mike, and he's going to talk more about the actual control scheme.
Perfect. Let's see. So this is not working. No.
The pointer doesn't show up.
It does light up the ceiling. It doesn't light up the screen, unfortunately. Interesting. So I will continue where Rob left off. I will explain a little bit on how the data from the analyzer are actually used to control the process, why that is relevant, and what other good use we have with that information and the value it brings. So as Rod mentioned, in a classic approach, there's a feed-forward and a feedback control loop in a sulfur plant. Feed-forward control loop only works on a flow measurement of the acid gas coming in that controls directly the main air control valve, which is the bigger valve of the two. Downside of that, it's rather sluggish control. It's a big valve, so even a small opening or a small closure of that valve has a big impact on the process, so introduces a big variation. The second control loop, the feedback control loop, typically would take the H2S or H2S over SO2 signal of the tail gas analyzer, the air demand analyzer, and uses that to control the trim air valve, which is the smaller valve of the two. That valve is able to respond quickly, but by the nature of the size of the valve, would only be able to control some 10 to 15% of the total air demand, meaning that if the change to the process is big enough, it actually is out of control pretty quick, and then if the valve is fully open or fully closed, you know, you're out of control completely. It's just not doing anything anymore. So that problem was solved already a long time ago by actually integrating the feedback and the feed-forward control loop by basically having the flow measurement of the acid gas as well as the tail gas measurement of the air demand analyzer interacting directly with the trim air valve only. That means that control to both a change in flow and a change in composition as measured in the back end would be swift, would be accurate. And we would use the main air control valve only to maintain the trim air valve in a position such that it actually maintains in its controllable range. So basically the position of the trim air valve acts as a set point for the main air valve to open or close. That is basically the situation before the introduction of a feed-forward gas analyzer. Now with the IPS4 analyzer, what we can do is measure the total composition of the acid gas coming in, being H2S, being CO2, ammonia, hydrocarbons, and water. Those are the 5 components typically found in SRU feed gas. We can normalize that and use that signal actually as a factor to respond to a compositional change of the feed gas coming in. In a traditional approach, the air demand defined by the gas composition would actually be set by an operator. It's a manual inputted value. So that could be either based on a simulation, on a predicted composition, or just because the operating procedure says it has to be a certain value and it has always been that value, be it accurate, true or not. So with the introduction of 2ACT, basically we introduce feedback signal from the air demand analyzer, feed-forward control from the gas flow, together with the feed-forward control from the analyzer into one integrated control where we can accurately and timely adjust the process air demand based on fluctuations in flow and composition. And basically, this is a further development of what was introduced many years ago as ABC Plus with ASAP. And I saw you there, sitting there in the corner, I think, yeah. I'm looking into the light, but... So basically, as Rod has said, we want to measure fast. Gas travels through the plant in about 30 to 40 seconds. So we don't have much time to actually respond to a change in the process. And that means a couple of things. First of all, we want to sample directly on the process line. We want to minimize, basically, sample transport from the process into the analyzer. So probe and analyzer are directly on the pipe. Second, we want the analysis to be fast, as Rod alluded to. Third, we want to create some residence time between the sample and the valve that responds to a change in gas composition. So we prefer the sample point to be as far as possible upstream of the sulfur plant. That could either be, on the top of a reflux drum in the amine regenerator, on the top of a sour water stripper column. But depending on where we have some space to put it, create some residence time to do that. And in order to combine it all together, basically we have something that real-time sets the air demand of the plant based on the composition of the gas coming in, basically every minute of the day, every second of the day. So basically what that enables us to do is now we have data of gas, compositional data going into the plant and data coming out of the plant. Almost all plants are equipped with a SAM system to report for permit purposes, the flue gases coming out, report on emissions. So if you have an analytical measurement of what's coming in, what's going out, basically you can close the sulfur balance around the sulfur plant. And basically especially important for people that report on sulfur recovery rather than absolute emissions, you can truly and accurately validate what actually the sulfur recovery efficiency is based on these data. Secondly, we're measuring what's going into the sulfur plant. Of course, that is the same in different words than in measuring what's coming out of the upstream unit, out of the amine regenerator or out of the sour water stripper system. So not only can we use that information to control the sulfur plant, we can actually also use that same information to troubleshoot and to optimize the upstream sour water stripper, the upstream amine plant. And the classic saying is if you have trouble in the sulfur plant, start by looking for problems in the sour water stripper and in the amine plant. So also for that purpose, this data is relevant. Having a more accurate control system also prevents upsets. The whole purpose is to have more accurate control and prevent some issues that people experience when they operate the plant without knowing what's coming in and the resulting error in air demand being supplied to the plant, basically. So basically, if you prevent upsets, you basically reduce the normal wear and tear on the equipment because of those upsets. So the reliability in principle goes up. The cost with equipment maintenance particularly would come down. And in the end, it also has a direct effect on emissions. As long as you stay within your operating window, you're fine. If your upsets are such that you slip out of that, you know, you could end up with emission violation and the potential fees that come with that. So basically the whole purpose is to optimize the control of the plant such that, you know, we're operating closer to what would be the optimal control set point of the plant. Clearly, an analyzer or a control system does not improve the theoretical maximum achievable capability of a plant, but it does enable operating more closer to it and thus reduce emissions accordingly. Illustrating that with a bit of a case study that includes a hydrocarbon upset in an existing facility. Basically, to describe what this is, every block is about a 2-minute interval. And the upper range on the top of the graph is 2% H2S coming out of the tail gas of the plant, which typically would be a trip setting of the plant. So what we were allowed to do here as part of an installation of a plant that had frequent upsets with hydrocarbon in the feed gas, basically this being a gas plant where multiple wells on a daily basis were either connected or disconnected, resulting in significant feed gas variations that operators have to deal with, not knowing or not being told which wells were shut in or which were opened, such that they had no clue of what was coming in. They installed a feed-forward analyzer to deal with that and actually capture and know these changes in composition. What they allowed us to do during startup, during commissioning, is actually inject methane directly in the feed gas stream. So what you see in the green line is that from a normal concentration of 0.9 volume percent of methane, total hydrocarbons, which is a fairly common number to be seen in a sulfur plant, is that number went up to 2.9% basically instantaneously. And to put that into context, that is about an increase in air demand of about 10%. And that is reflected in the blue line, where you can see that based on the compositional analysis, the calculated amount of air to be put into the plant per the ratio of acid gas going into the plant was 1.35 before the hydrocarbon event and 1.47 after the hydrocarbon event. So basically, instantaneously change in air demand of 10%. The red line actually shows the response of the control system reflected by the signal from the tail gas analyzer. So you can see that it starts to respond the moment that the hydrocarbons are introduced. There is an upswing followed by a downswing, and basically in 2 or 3 swings, the system is back to the line where it all began, not exceeding a maximum value of about 1.4, which is far removed still from the trip setting of 2.0, evidencing basically that the system is able to maintain control of the system throughout the event. We move to the right a little bit, and basically what you see is that after a while, after about 10-12 minutes, hydrocarbons were removed from the system again. The injection basically was stopped. So this reflects not a 10% upswing in air demand, but basically a 10% reduction. Again, evidenced by the air demand change in the blue line. And you see basically the same result of the system response reflected by the red line. So clearly, demonstrating that a feed-forward control loop can bring a benefit to SRU operations in case of fluctuating feeds. So what 2ACT basically does, it ensures stable operation during compositional change of acid gas and sour water stripper acid gas feeding into it. Basically, it ensured that in doing so, we have very fast and accurate response of the air control to adapt to a change in feed gas flow and feed gas composition. It also does that basically during startup and shutdown, where the feed gas composition going into the plant may not typically be known, but because we now have an analyzer, we can actually see what it is. So, in fact, we can already prepare the controls to properly respond to what we're about to introduce into the plant before we're doing it, so we can be proactive. And also, having this system, we minimize or reduce operator intervention for two reasons. One is the air to acid gas ratio would be a manual set point before, so may from time to time have to be adjusted by operators. This is now automated. Secondly, because we have more stable control, this would result in lesser alarms, lesser upsets, and lesser operator interventions, actually freeing up time for the panel operator to focus on other plants that are also in his or her span of control. So, in the end, because of this, like I said, we're able to closer operate with the optimum set point of the plant. So this would reduce emissions, or in case of severe upsets, reduce flaring. It also reduces the wear and tear of the equipment. It reduces, therefore, the downtime due to unplanned shutdowns, or in case of plants that were restricted by these fluctuations in feed of using their maximum throughput capability, actually frees up capacity to produce more acid gas. So basically, if you bring this all together, and to wrap it up, because I realize we are the last presentation of the day, so probably, you know, we are between yourselves and reception later on. But in effect, combining the IPS4 analyzer with this type of control system, we provide a robust and accurate and fast air control to a sulfur plant at a relatively low cost. I mean, if a plant is restricted in capacity, or in case of an upset or an emission violation, would have to reduce in capacity in the refinery or the gas plant, then, you know, the cost of that are significant. And in such a situation, return on investment by installing a fairly straightforward feed-forward analyzer plus control loop, you know, the return on investment of that is pretty fast, could be as fast as a day. Also, in today's world, where, you know, there's a focus on energy reduction, where there's some ESG reporting on CO2 emissions, on carbon footprint, it's an elegant way actually to reduce SO2 emissions, to reduce carbon footprint in an existing asset. So also there it fits quite nicely. And with that, I'd like to wrap it up, open it up for questions if there are any. And if you want to have all kinds of technical details on the analyzer and the analytics, please go see Rod at booth number 312 it is. We'll be happy to explain more.
Any questions?
I see one over there, yeah. So the question is there a oxygen analyzer on the stack, and does that impact? There is an oxygen analyzer on the stack for a couple of reasons. Typically any waste gases passing through a sulfur plant, passing through a TGTU, any sulfur components, they are combusted in an incinerator to SO2. 100% with an excess of air. So basically the oxygen analyzer is there to ensure that you have an oxidizing environment in what we call the thermal oxidizer. So the oxygen analyzer is installed in the control loop for the incinerator. It ensures excess oxygen. It ensures if you have H2S limitations in the stack, for example, that you meet those. Otherwise, it is not a factor in the control of the upstream sulfur plant itself.
Any other questions? All right, good job, guys. That concludes our today's paper. Don't forget to fill out the survey forms. The banquet hall will be open till 6:30 today, and we reopen tomorrow at 8 a.m. Thank y'all.